All right, we're starting chapter 2, and in chapter 2 we're going to look at atoms in the periodic table. So what I want you to do is, whenever you're doing chemistry from this point forward, make sure you have a periodic table in front of you. You can find one in the inside front cover of your book, or you can photocopy one or get a commercially available one. Anything is fine. You will be given a periodic table to use during any exam, so you don't have to memorize anything on the periodic table. Periodic table is a handy tool that chemists use all the time and keep them nearby for reference. Chapter 2 looks at how atoms are put together with subatomic particles, and then we will start putting atoms together in molecules. But the first thing we're going to do is just look at the atoms and how they're put together. The elements are found in the periodic table. The symbols for the elements are found in the periodic table. These are the basic building blocks of matter. All matter that we find on Earth is made of these elements. These elements are represented by a symbol which is written with the first letter capitalized and the second letter lowercase. You must follow this method for clarity. You can get very confused if you use all capital letters or all lowercase letters, as you may not be writing what you mean to write for others to understand. For the first exam, I expect that you know the symbol only of the first 20 elements. All you have to know is that Ca, for instance, stands for calcium and C stands for carbon, and know the difference between them. No other information needs to be memorized. For the remaining course, you will be expected to know the majority of the other symbols, although we will be using primarily common elements, not rarely used elements like niobium and maybe hafnium and things like that. Those are rarely going to. Atoms are the little individual pieces of elements. This is our atomic theory, is that elements are made up of little bitty units that are essentially the same as each other, and we call them atoms. If I take a sample of iron and look at the smallest piece of iron that is still iron, we call that an atom, and we visualize it to be a little round ball. Now, these atoms can combine to form other substances. For instance, carbon dioxide is a combination of carbon atoms and oxygen atoms. And in one molecule of carbon dioxide, we have one atom of carbon and two atoms of oxygen. We consider atoms to be indivisible. However, they can be broken apart in nuclear reactions. But we're not going to be worrying about nuclear chemistry until we get to that chapter. For now, we're going to consider atoms to be indivisible. They are imagined to be something like little tiny balls. We cannot see atoms, but we can detect their electrical fields with something called a scanning tunneling microscope. And when we do detect their electrical fields, they do appear to be little balls, but they are very tiny and we cannot see atoms with light. They're so tiny that a drop of liquid helium will hold this number that I show you right here, atoms of helium. Now, I'm going to convert this to scientific notation for you, which is something that you need to learn how to do. If you're having any trouble with scientific notation, I'm hoping you already know how to do scientific notation. But if you don't, there's a good description of this in the book, and you can come to me for help. I'm going to convert this number to scientific notation, and to do it, I count 3, 6, 9, 12, 15, 18, 21, 22. 22 zeros, so I'm going to make this 2 times 10 to the 22 atoms of helium in a drop of liquid helium. That's a lot of atoms. This number is incredibly large. This number has a positive exponent, 2 times 10 to the positive 22, because it's larger than 1. Numbers that are less than 1 have negative exponents on their 10. When we combine atoms with each other, they either form molecules, which are discrete units. For instance, right here, this is ribose. Ribose is a molecule in that when I look at the smallest entity of ribose, it is the same as every other entity that's in there, the smallest unit of ribose, what you find is it's made up of 5 carbons, 10 hydrogens, and 5 oxygens connected to each other in a specific way. Those are molecules. They're individual units that can move apart from each other. Some compounds do not come that way. Some compounds come as a crystal lattice so that they're present in a ratio only. An example of this is sodium carbonate. If I get a sample of sodium carbonate, what I will find is there is a ratio of 2 sodiums to 1 carbon to 3 oxygens in that compound. But I cannot get a unit of sodium carbonate which has 2 sodiums, 1 carbon, and 3 oxygen. It exists as a crystal lattice, and so you can't get that one individual unit from it. We'll talk more about this when we go into bonding. Atoms are made of subatomic particles. The subatomic particles are electrons, protons, and neutrons. Neutrons and protons have masses that are approximately 1 AMU. An AMU is what is called an atomic mass unit, and it is the approximate mass of a proton and a neutron. We define it more precisely later on in the course. Protons have a positive charge and neutrons have no charge. There is a particle called an electron that has a negative charge. Electrons are considered to have no mass for most things that we do in chemistry. Sometimes we do consider their mass because when we get very precise in calculating mass, we have to consider the mass of an electron. But when we're just doing the average things in chemistry, we just consider electrons to have no mass because their mass is so small. If you look at this mass right here, 1,800 electrons will be the same mass as 1 proton. Atoms are made up of protons, neutrons, and electrons of approximately the same numbers, so the majority of mass comes from the protons and neutrons, and these electrons contribute extremely small amounts of mass to the total atom. So for the most part, we just ignore what mass they have. The key thing for you to remember from this point on is that electrons have a negative charge, protons have a positive charge, and neutrons have no charge, and that the masses of a proton and neutron are 1 AMU apiece. Electrons essentially have no mass. Charge is the most important characteristic of those subatomic particles. Charge is what gives us the structure of the atom and the behavior of atoms and the behavior of molecules and how reactions occur. There are 2 principles you need to know. Like charges repel and unlike charges attract. This means that electrons repel electrons and protons repel protons, but protons are very attracted to electrons. Neutrons have no charge, and so there is no attraction to protons or electrons with them. Of course, we're going to find out that protons and neutrons are in a nucleus, and there are strong forces that hold them together, but we're not going to be worried about nuclear forces at this point in time. The structure of an atom is so that The protons and the neutrons are in the center of the atom, and we call it the nucleus. Because there are only protons and no electrons in the nucleus has a positive charge. It is an extremely tiny part of the atom. If a nucleus is about the size of a softball, the electron cloud would be a couple of kilometers wide, very, very large. The electrons make up the rest of the atom, and they are surrounding the nucleus, and they determine what is the outside edge of the atom, because they are what are on the outside. The protons are attracted to the electrons, and so they pull the electrons toward the center, toward the nucleus. However, electron repulsion keeps the electrons from getting too close to each other. The electrons in one atom will be repelled by the electrons in another atom. So when two atoms are made to be adjacent to each other, the electron clouds repel each other, so the two atoms don't actually join together, the nuclei joining together and the electron clouds then becoming one. So two atoms remain discrete units when next to each other. The identity of an atom is determined by the number of protons. If I have an atom of sulfur, I can look on the periodic table and see that it has an atomic number of 16. That 16 tells me that there are 16 protons in that nucleus. If I pick up an atom and I find that that nucleus has, let's say, 12 protons in it, then I know I have a magnesium atom. The number of protons, which we call the atomic number, is the identity of the atom. It determines what element you have. Atoms are neutral. So that means that the number of electrons must be equal to the number of protons. What I'm trying to say is that, let's say we take a sulfur atom. A sulfur atom has 16 protons in it, but a sulfur atom is neutral. 16 protons is 16 positive charges. So that means that a sulfur atom must have 16 negative charges in it, or 16 electrons. The number of protons is very stable and are very hard to change. It requires a nuclear reaction to change the number of protons, and so it does not happen very easily. It takes a great deal of energy or energy release to change the number of protons. As far as we're concerned, until we get to Chapter 9, the number of protons never change. So if you pick up an atom of potassium, it remains potassium as long as you are dealing with it. Protons are very hard to change because they're down deep in the nucleus where they're held very tightly, and there's a huge energy change in order to change the number of protons. However, electron numbers can be changed with relatively easily compared to changing protons. Nonetheless, it does require energy. Let's take fluorine. A neutral atom of fluorine is 9 protons and 9 electrons. If I have an electron taken away from a neutral fluorine atom, it gives me 9 protons and 8 electrons. That means there are 9 positive charges and 8 negative charges. More positives than negatives gives a positive charge. So we write the symbol for an atom that has 9 protons and 8 electrons as fluorine positive, or we can write fluorine 1 positive. This is an example of the formation of a cation. A cation is a positively charged ion. An ion is any atom that has charge. A cation is a positive ion. In a cation, you have fewer electrons than protons. That means more positive charge than negative, so overall a positive charge. An electron taken from an atom can be given to a neutral atom. That gives more electrons than protons and a negative charge. An ion formed in this manner is called an anion. An example would be neutral fluorine is 9 protons and 9 electrons. If I take an electron and give fluorine an electron from another atom, then you have 9 protons and 10 electrons. There are 9 positives and 10 negatives, which gives us fluorine with a negative charge, which we often will write fluorine 1 negative. This ion here, because it has a negative charge, is called an anion. Let's look at some examples of some ions here. If I look at silicon, silicon has 14 protons and 14 electrons when it's neutral. If I take away an electron, you can see 1 electron has been removed. Well, then silicon has a 1 positive charge. If I take away 2 electrons so that it only has 12 electrons, then silicon will have a 2 positive charge. If I take silicon and add an electron to it, well, then silicon has a 1 negative charge. If I add 2 electrons to it, so it has 16 electrons now, then silicon has a 2 negative charge. All of these are ions. These two with a positive charge are cations, and these two with a negative charge are anions. Notice the only thing changing on these atoms right here, or these ions, is the number of electrons. The number of protons gives it its identity, so throughout this, the atom is remaining silicon.